everyone, welcome. We give it one more minute here for you guys to join in. And then we will talk about our webinar, Zener Barriers versus IS Isolators. We picked this afternoon time for European time. So it's morning time in the US. And so we hope for more people from the Americas to join in. We had a good numbers of registrants. We had some questions. We are posed through the registration process. We will answer those at the end of the webinars, and we will also answer some other questions, any live question you guys might have. Okay, so should we start or?
Sure.
Okay, let me close this box so it's clear for me. Okay, so I Bob, and before we start, let me welcome you guys and this webinar on Zener Barriers versus isolated barriers. And as I said, we collected several questions. We'll be able to answer those at the end. And you also are able to post questions throughout the webinars using the question and answer box. Let me take a moment here to introduce Bob. For those of you who have not met him before, he's our guest and speaker for today. Bob has over 30 years of experience in the EX world. In fact, he's a CompEX instructor as well as an instructor of the ICEX CompPC scheme. And he's also an inspector and a member of US ULSTP committee. So, you know, he's very, very qualified. Together we've done many webinars and, you know, to date, has not been able to find him on the spot, you know, always has an answer to every single question you guys can post.
I don't know about that.
Yeah, well, we'll see. I'm Paolo, you know, you guys know me. I'm VP of Sales of GMI, so I'm bound to give you a few minutes rundown of who is GMI and what we do and why we do it. So our company we design, engineer, and manufacture a complete range of intrinsically safe and certified devices for automation packages such as DCS, fire and gas, EEPS, marine packages, and so on, in several industrial sectors, from oil and gas to food and beverage. We have over 40 years of experience in the market and 100%, very proud to manufacture our product 100% in our headquarters near Milan, Italy. On the other hand, we are global players with presence in all the continent. In fact, we have next up over 10 direct offices and 75 plus distributors around the globe. We're about 200 super dedicated team, and we run many functional safety, EX now, and cybersecurity courses throughout the year. With the COVID pandemic, you know, ongoing, we have forced to do those online, but we can do those online today. We can do complete courses, including certification, including exam online. And we have thousands of installations around the globe. What we do high-tech products that are in our facility. We have full product traceability. We do 100% testing on every single element, and we offer 5 years warranties and guaranteed of availability up to 10 years. And so we basically design high safety critical components, and we take special care in doing so because we care about, you know, the environment we live in and the people that occupy it. Okay, Bob, next. So, this is a new one for me. Okay, yeah. So we have we comply to all standards and regulations. So we have many certificates. As you can see on the right there, we have the logo of all the certification agency we have. I mean, there are too many to mention. I guess we have some there. We have TUV, Functional Safety Management, up to C3. So our company, not only our product, are certified for SC3. Of course, ISO 9001. We have ISO 45000 for occupational health and safety. We have ROS and REACH compliant, 3TG, I mean, code of ethics, anything you want, we have to have anyhow. You're committed, you know, to try to be a good company. So here we have our product we manufacture, IS Barriers, safety relays, with and without line monitoring. We have also isolators, which are also SEAL certified, up to SEAL3 certified. We have power supplies, which are EX and SEAL certified. We have multiplexer, heart multiplexer, temperature multiplexer, digital multiplexers, a series of termination boards, which are designed to interface with the most common system out there. SPD or surge protection device, loop indicators, and of course we have a division that runs these cybersecurity courses and services, as I mentioned earlier. Some of our customers, you have all the system vendors from maybe to Yokogawa, not mentioning all the rest. We have many EPC with whom we have done project together, and we are very proud to list a lot of OEMs among our customers, people that make drilling rigs, any sort of equipment that is mounted out in the field. You know, guys, if I'm a little grungy today, you have to excuse me. I was for 1 month locked in my house due to my COVID condition, which I just got over last night. So I'm okay. Everything went well, but I'm still a little, in a month basically at home in bed, not doing much, Anyhow, so end users, we are in the AVL of many end users, and I believe this is my last bit for today. Okay, so we are here now talking. I'll let Bob talk you guys through the webinar. As I said, there's a question and answer box there. You can click there and answer, pose your questions, and we'll see if we can answer it. Okay, Bob. Okay. Disappear here from the webinar and just looking at the question and answer.
Okay. Well, thank you, Paolo, and thank you, everybody, for joining us today. Yeah, and Paolo, I'm really glad to hear that you're doing much better. So for all of you folks around the world, hope you're all doing well. Fortunately, here in Texas, our COVID rates have gone down, and we've opened up a lot of things that are going on. So hopefully, the same thing is happening in your part of the world as well. So
yeah. Let's hope we all, some of we were hit first, and so we are coming out of it earlier. Than some other countries like India today. It's a disaster, unfortunately.
Yeah.
For them. Yeah.
Well,
for the best. Okay, let's go on.
So we'll talk a little bit about the different kinds of intrinsic safety and basically the two major types. But before we get into that, we just want to talk real briefly about an explosive atmosphere. So I know some of the questions that we had that some of you guys asked, and we'll try to address some of these as we go along. But people ask, usually one of the big questions people will ask is, of the various protection concepts that are available out there, which is the most common, which is the most prevalent? And it is very difficult to kind of answer that completely, but intrinsic safety is one of those design systems, if you will, or protection concepts that has been around for an awful long period of time, but there's an awful lot of confusion when we use intrinsic safety. There's misinformation out there, but it is, when it's used properly, it is absolutely one of the safest EX protection concepts out there. But as we talk a little bit about protection concepts, we need to talk about, obviously, an explosive atmosphere. So an explosive atmosphere is an area in which we have flammable substances. They could be gases, vapors, dust, fibrous lines. We typically are going to have air or oxygen, and then we're going to have some sort of ignition. And that source of ignition could be electrical sparks. But the other thing that we have to remember with sources of ignition, there are multiple different sources of ignition that we can run into. Everything from static buildup to obviously an open flame, obviously electrical arcing and sparking, exothermic reactions. There are a bunch of different potential sources of ignition. So it's not just the electrical arcing and sparking devices that are in industry that we need to be concerned with. So the important thing is that when we think of all the various protection concepts, we really have to kind of focus our attention on the ignition source, because we're assuming that we're putting our EX equipment into an environment in which oxygen is present. If we remove oxygen completely from the environment, then obviously it's a very difficult place to work. So we really focus our attention on the ignition source, or we focus our attention on reducing the amount of gas, vapor, or dust present into the environment. So the various concepts that are out there, the protection concepts, we basically divide it into three different major principles. So segregation, where we're in effect removing potential flammable gas atmospheres, or from the arcing and sparking or heat producing devices. That could be, oh, I apologize, I'm going to mute that. Segregation could be where we're encapsulating it maybe in a resin. We could do oil immersion, or pressurized panel is a good segregation concept that many people are familiar with, where we're basically making sure that there's no flammable gases on the inside of a panel coming into contact with arcing and sparking. Now, flame-proof, a very common concept, is the concept of containment, where we're assuming we're going to have a gas vapor oxygen combination get on the inside of an enclosure. One of the misconceptions out there in industry is flame-proof enclosures are somehow gas tight, and they aren't. They will actually allow gases and vapors if it's outside of the enclosure. Due to normal heating and cooling, we're going to have this constant movement of gas and vapors from the outside to the inside and vice versa. So flame-proof is containing an explosion on the inside and making sure that doesn't propagate to the outside and cause more damage. And then finally, there's prevention, and that's where increased safety and intrinsic safety come into play. So prevention is basically removing, in effect, any potential arcing or sparking. And we do that by the use of increased safety enclosures with creepage and clearance distances, and with intrinsic safety, where we're limiting the amount of energy. So these are the basic concepts. Now, there are other protection concepts, but they all pretty much fall within these concepts, if you will. So talking about intrinsic safety, it is one of the most flexible and cost-effective solutions, and it has been standardized for many different applications. I know many of you are located in various parts of the world. It is referenced within the IEC standards and the 60079 standards. There's two different standards on intrinsic safety within the 60079 series. One is, I think it's 11. I always get it mixed up. And the other one is 25. So those are the two standards on intrinsic safety. 11 is the standard that deals with how to build a barrier, so to speak, and 25 has to deal with the design of a system. But here's the important thing to remember on intrinsic safety. You really need to look at the entire loop, if you will. Because we basically take a barrier, we take our field apparatus, we take a look at the cabling, we look at our incoming power that's coming from our control room, and we look at this as a system. And so intrinsic safety is a true system concept. And it's actually one of the few, if not only, true electrical protection concepts. Almost all the other protection concepts are mechanical in nature. Intrinsic safety is actually an electrical concept. So we call these basically intrinsically safe barriers, or sometimes we call them barriers. The common terms, ISBs. And basically, it's pretty much around the world, we call them the same thing, if you will. We use the same verbiage in the United States, Canada, as we do in Europe and in the IEC world as well. So what is intrinsic safety? So again, it's preventing a potential ignition from taking place. So based upon that, it is limited to low power applications. So where we don't see intrinsic safety is where we have high power applications. We don't see intrinsic safety with, say, motor starters or motors. We don't see typically intrinsic safety with lighting products. But when we start talking about our sensors, our devices that are used to actually monitor and potentially control other electrical or other mechanical equipment, that's where intrinsic safety is typically used. So it's low power applications. There are safety factors. There are design characteristics on the components with the infallibility and redundancy that is built into it. There's also some requirements for isolation distances. And of course, there's the requirement for actually using a barrier. So the applications, again, electronic instruments, measurement and control processes, battery supply devices. So anywhere where you're basically looking at low voltage, 12, 24 volt DC type circuits, in many cases, that's a very good application potentially for use of intrinsic safety. Now, there is alternates to not going intrinsic safety, and some people don't use intrinsic safety. You will find, for example, you'll find transmitters that are rated EXD, that are flame-proof. But you'll see a transmitter that can be done either EXD or EXI, and you have to wire it up accordingly and design it accordingly to the protection concept used. Now, some people will say, hey, I want to use a 4 to 20 milliamp Emerson Rosemont transmitter. You can certainly do it and do it as flame-proof, for example, but you have to make sure that the glanding, the cabling, and everything else is suitable for that application. Where under IS applications, in many cases, the cabling, the glanding, the installation requirements are not quite as rigid. So potentially you can save some money by adding a barrier and decreasing some of the things that you would actually have to do to make it a full flame-proof system. So there are some commercial advantages for using IS besides just the safety standpoint, plus the ability to work on the system. So there's your loop. You hear this term a lot in the intrinsically safe world. You'll find what is called an intrinsic safety loop. Sometimes you'll hear the term what is called a descriptive system document or a control drawing. These are all basically kind of saying the same thing, but we're talking about, in effect, kind of like the last slide, we look at our apparatus. We could have simple apparatus. And by the way, what a simple apparatus is a non-energy storing device. So things that are normal things like switches, that is not energy storing. An RTD could be a simple device. However, there are devices that will actually be powered, say like a transmitter or potentially a solenoid valve or something like that. That is actually considered to be an IS apparatus, a non-simple device. Then we take a look at our cabling. Then we call the barrier, another term for that is called the associated apparatus. That's the terminology that we use in our safety loop. We call a barrier an associated apparatus. And then, of course, the feed that's coming in from our instrumentation circuit. So that's our intrinsic safety loop, or what we would call a control drawing, or potentially a descriptive system document. So there are two different kinds of associated apparatus that are commonly used in the marketplace. I wouldn't say the most common, but the original was the Zener Barriers. And we would typically call those barriers. That was kind of the first, that was the first intrinsic safety design. And IS was developed many, many years ago in the mining industry, where they used it for protection of signaling devices in the mines. So Zener barriers are passive devices, and they basically don't switch on, if you will, until we have a fault condition. And the Zener diodes open up and they divert any of that excess energy to ground. It's very important that we have a good ground. Now, isolated barriers were a technology that was developed years later. They've been around for a long time now, but up until really about 20, 30 years ago, most of the barriers you would find on the market were Zener barriers. Now we find many different manufacturers are manufacturing isolated barriers or isolators. Now these are active components and they have a safety isolation. And typically this is a transformer or optocouplers to keep a fault energy to pass from a safe to hazardous location. So we're actually, in this case, we're mimicking the signal from the control room out to the field device, and we're using the protection of a transformer or optocoupler to keep a potential fault condition from traveling down that loop. So this talks a little bit about safety, flexibility, installation cost, maintenance cost. Again, intrinsic safety is one of the safest concepts out there. Purging and pressurizing is very safe, certainly. Explosion proof, when it's properly done, is certainly safe. The issue is on explosion proof or flame proof is typically the maintenance or the damage to potential flame-proof products. If we don't treat them very, very carefully, we sometimes have issues. And when we do inspections, we see an awful lot of issues with flame-proof or explosion-proof. Flexibility, intrinsic safety offers a lot of flexibility. Again, installation costs, maintenance costs on IS is actually extremely nice, if you will. One of the big benefits on intrinsic safety is that actually, per the standards, you can actually do a lot of your maintenance on intrinsic safety loops while they're energized, live, if you will. Now, some clients will say, no, we don't allow that, but the standards actually do allow you to do a lot of maintenance on intrinsic safety while it's live. So we have a poll question. We don't have too many poll questions.
Yeah, okay.
But
so
what is the basic?
Talked about several protection methods, and you introduce IS and differences that protection method introduced with others. So we have a basic question for you guys to see if you have followed us so far. So what is the basic protection principle of IS? Is it isolation? Oh, sorry, I need to launch poll, otherwise you cannot do anything. You see, I told I'm still groggy. Isolation, mitigation, segregation, prevention, or containment. You know, there's no judging. We just like to see if you know what we're talking about. So keep in mind that IS, as Bob was saying, that we have two basic solutions, which we will introduce later. The differences between an isolated barrier and a Zener barrier, which is a non-isolated barrier. So one of those questions which I see some of you are answering is not a good one. Because we have Zener barriers which are non-isolated and they perform IS. But I see most of you have answered correctly. So we'll end the poll and show you the result, and then you can go on.
Yeah, so yeah, we say isolation, and we talk about isolation barriers, but yeah, as Paulo said, the correct answer is prevention. So we're limiting the amount of energy that's going into a hazardous area by the use of intrinsic safety. We have one question that just popped up, and
the question says, stop. Okay, you don't see the poll anymore, right? Or do you see it?
I don't see it. Hopefully, I don't.
You saw it for a moment there, right?
I saw it for a moment. Yep.
Yeah. Okay. So stop that. So the question is, if there are devices designed especially for gas analyzer sensor, where the transmitter is EXT and the sensor is connected to the transmitter is EXI. How can you recommend installation and wiring? Well, I guess when you have a combination of IS and EXT, as you were mentioning earlier.
Well, yeah, generally what you will see on transmitters, they will be certified. Again, they will have a certification that says, hey, you can install this as EXD. It'll have a certificate around that. And then you might find another marking on that exact same transmitter, or it could be, you know, you buy it from a company and they supply it. If you wanted IS, then it comes in with the IS label. You buy it with EXD, then it's an EXD label. The housing itself is basically the same. They make a small little flame-proof housing. So what's the real difference between the transmitter, if you will? The cost differential really isn't any different for the transmitter itself. Then it really comes into play about the cost of your cabling, the installations, the cost of the cable glands, the addition of an intrinsically safe barrier. Obviously, the wiring issues that you need to take into account when we're doing IS with regards to segregation to other circuits by the use of shielding or separation in trays. So it's not just a real simple to say, hey, look, if we go IS, we're going to save 20, 30%. It may be that case. It may be a wash. In some cases, it could be more. It's based upon the fact that you have to take into account the gland and the cabling and the cost of the barrier and what you need to do with an IS loop, as opposed to going to a full EXD type system.
Yeah, Bob, I think, you know, in some cases when you have this type of EXD transmitter, which are complex and require a lot of power to operate. Therefore, they cannot be powered through a barrier because they need more than 20, 30, 50 milliamps, and maybe they need a couple of watts, 3, 4, 5 watts. So they need power. Then they are EXT designed, but the sensor element might be connected IS. But in this case, the IS interface is within the box, within the transmitter. The transmitter itself, as part of the circuit, is IS certified. So, and I've seen, I'm not 100% sure, but I think the wiring going to that sensor is probably EXT anyhow. You can use an EXT wiring method for an IS, right? I mean, the EX conduit seal, it's overprotecting, but you can do it, right?
Yes, I mean the requirements on IS with regards to cabling and wiring and everything else, you cannot run IS circuits and normal instrumentation circuits within the same cable itself. You would have to run multiple cables, which would mean multiple entries into a device or something like that. You would just you couldn't combine IS and non-IS within the same cable.
Yeah, of course.
So, and then you also have to indicate your cables that they contain intrinsically safe circuits. And the common way of doing that is using a light blue jacket. That's not a requirement that it has to be light blue, but that is typically what is done. But you would have to have something on that cable to tell you that that does contain intrinsically safe circuits. So yeah, you could have a combination of flame-proof and intrinsic safety with a single device, if you will, and that's not terribly uncommon. And you would wire it up in effect.
For example, you can think. I'm thinking of remote I/O solutions, where you have an EXT type power supply or an increased safety type power supply, depending if it's Division 1 or Division 2 installation, because the power supply for remote I/O is a big block, but then the remote I/O blocks, the analog input, digital input, the various modules that are all IS certified. So the input on the wires going to the field is IS. But on this side, going back to the control room, you have the EXT conduit.
Yep.
Okay, let's move on. Okay, so here's the heart of our discussion: Zener barriers versus isolated barriers. So first, let's define what they are.
Yeah. So this is a if you will, a cutaway of a typical Zener barrier. And all manufacturers will basically, regardless of the manufacturer, it'll be the circuit will be set up very similar to this. So what you have, in effect, you have, and I'll see if I can actually highlight this a little bit. So we have a fuse here located at this point. We have a current limiting resistor, an infallible resistor. And then we typically will have Zener diodes. And actually, in this particular drawing here, we see that there's actually 3 Zener diodes. Just by looking at this drawing, I know that this particular Zener barrier is actually suitable for zone 0. It's an IA barrier because it has redundancy, and that's a requirement. So if it only had 2 Zener barriers, or excuse me, 2 Zener diodes, we know that this barrier's circuitry is an IB circuit. If it had a single one, it would be an IC circuit. But it's basically set up in this fashion. So if we had a fault condition, what would actually happen is that as we have an increase of energy, if you will, we hit our current limiting resistor. As the voltage increases, Zener diodes will open up. So these Zener diodes will be rated, say, at 28 volts or 29 volts or 30 volts or whatever it is, that voltage, the maximum it is. Once it starts hitting at that level, then that excess voltage is going to be driven to ground. And that will work. And at some point in time, if left unchecked, what will happen is that obviously the current limiting resistor potentially could blow, or the fuse could blow. So at no time do we have any potential problems over here, okay? So we don't have any issues with regards to our final end device where we have an excess of energy going into the hazardous area. But notice this, 1 ohm max, good ground connection. This requirement is pretty much worldwide, 1 ohm max resistance of our system ground. Notice that this ground here is considered to be our IS earth, or a clean earth. We don't want to have this earth tied in just to all of our other tied in earth points within our facility, because we can all of a sudden hear all kinds of noise and all kinds of stuff that could come right back up into our system and defeat the whole purpose. And also, obviously, if we don't make this connection, then what potentially happens, we could have a fault condition that could travel down this leg and do something there. So there are some very key important things to remember when we're using Zener diode barriers that we have to keep that in mind when we're using. Now, an isolated barrier, if you see it, it looks very, very similar. We have, again, a current limiting resistor. We have a fuse. In this case, it's protecting the safety transformer. And notice that we have in the middle here our safety transformer. So what we're doing, we're basically taking this signal that's coming from this point and it's transferring it on over in this fashion and mimicking or sending that signal back out to the hazardous location. Notice this here, there is no need for a safety ground, okay? We may need to ground our isolator onto just a DIN rail, but normal earth, but we do not have to have a dedicated safety ground for a galvanically isolated barrier. So that's an important point to remember. So under a fault condition, I already kind of mentioned this a little bit, but if we had a situation where we potentially could have that fault current, we could actually potentially have it go to ground in the hazardous area. If we don't have a good ground in our IS circuit at the point located within the hazardous area, and certainly if we don't have a good ground connection outside of the hazardous area. So this is kind of the big problem, if you will, for Zener diode barriers. And a lot of people have gone away from the Zener diode type products to go more towards an isolator type products. If you think about it as an example, I mean, in many cases, if you're building a skid package and you're using Zener diode barriers, you have to have some sort of dedicated IS earth. And how do we know that if we're going to send that skid package out to a client that's out in the middle of nowhere, that, you know, they've got a good, clean, dedicated earth? We can put all the warning labels and everything else, but if they don't tie it into a good, clean, dedicated earth, that's a big issue. So when we look at an isolated barrier under a fault condition, what happens? It hits the transformer, it stays into the safe area. We never have a point where, if, say, for example, the cable was cut or something like that, where we had a fault condition within the hazardous location, because our safety transformer, in effect, has limited the current going into the hazardous area. So, as you might expect, if we look at the architecture of a Zener diode barrier and we look at the architecture of a galvanically isolated barrier, which one do you think costs more, right? Well, typically a galvanically isolated barrier does cost a little bit more. It used to be significantly higher, but as time has gone on, people are going away from Zener diode barriers and going more towards galvanically isolated. More manufacturers are doing it. The volume is growing, therefore cost of manufacturing is coming down. So nowadays, actually the cost differential between a galvanically isolated product versus a Zener product, while it is still more expensive, it's not as dramatic as many people, even from 10 years or so ago. The other factor that some people don't think about is obviously the cost associated with having that external ground, that safety ground, and making sure that the cost associated with installing that, maintaining it, doing all that, you have to take that into consideration as well. So here's our Zener barrier grounding. This is also something that many people will actually do. You notice in this case, we actually have two ground connections, right? We have our safety ground connection and we have our redundant safety ground. Now, it is actually a requirement that we're supposed to periodically to check the resistance of our ground. Well, the moment that we remove one of these ground legs to check the resistance on our ground, we now have a dangerous potential situation. So it is good engineering practice to actually have a redundant safety ground that is basically separate from our normal safety ground. It's our redundant, so we can actually check the resistance of our safety ground periodically. So that's very good engineering practice. It's not necessarily something that must be done. It is good engineering practice, and it is commonly done, if you will. Oops, close that. So again, independent grounding, this is a potential fault condition again. So this is where we really want to pay attention. That's the important thing to take away from this webinar today is I don't want to tell you don't use Zener barriers, but let me say this, GMI does not manufacture Zener barriers. GMI only makes isolated barriers. And I believe in isolated barriers myself. I think they're much safer. I think they're much more robust. And it's a better system. And there's less things that potentially can go wrong. However, if you do use Zener barriers, the important thing to remember is pay particular close attention to the potential fault conditions that we can see in using Zener diode type barriers.
Well, as you mentioned, Bob, so we might be a little biased, but we have not biased the presentation here. It's everything is a fact, and we had a question on voltage. We can run how many volts we can run through a barrier. Basically, it depends. There's a curve. Right?
Right.
It depends on it's a power issue. Voltage and current combination. So you can run high voltage, very, very low current or combination. Typically, you have a 24 volt DC power, also 5 volt, 12 volt, 48 volt.
Yeah,
there's a limit.
Right. Yeah. So it is a combination of the voltage and the power. So this is something, if you're not familiar with, as I do inspections. Part of the inspection process is that there are some requirements when we do inspections on intrinsic safety. These are some of the things that we look at, right? So table 2 within this 60079-17 standard, that these are the things that we look at under a detailed inspection. And I'll just show you this. So this is what is called a detailed inspection. This is a close inspection, and this is a visual inspection. So when a piece of equipment gets built by a manufacturer and before it gets put into service, it must go through what is called a detailed inspection. When we look at installations for IS, obviously these are the kinds of things that we're looking for, but pay attention to this, right? Earth continuity is satisfactory. The connectors are tight. Earth connections maintain the integrity of the type of protection. Intrinsically safe, earthing is satisfactory, insulation resistance is satisfactory. So these are the kinds of things that we actually must do. And if we're building skids or building packages that incorporate intrinsic safety, and you have an inspector come in and say, hey, we want to look at what you've done, this is the stuff that we're going to be doing. We're going to look and we want to check this information out. So it's important to understand this and be aware of this. That we do this, and these are the reasons why we're doing this, and that's why earthing is so important. Now, just to kind of summarize a little bit, galvanic isolated versus Zeners, there is no safety ground requirement, better overall accuracy, lower installation cost, right? When we start taking the cost of the barrier, but then we don't have to worry about the earthing and grounding, then the installation cost can be less. Of course, Zener requires that dedicated safety. There are the routine checks. There are some potential issues on Zener leakage accuracy. So there's pros and cons of both. And again, I think you're probably all aware of, the major pros and cons. One of the other things that I know people in the past really complained about, if you will, with the use of galvanically isolated barriers is generally they were much larger than Zener barriers. And that was absolutely the case. The density of Zener barriers, typically because you didn't have that safety transformer on the inside, you could make them much thinner. You could get more of them densely into a panel. The advent, however, of galvanically isolated barriers have come quite a long ways. And now we can actually do things like 4 channels in a single barrier. And the actual width of these barriers now is significantly less than what they used to be. So people that would argue to say, hey, look, I can't use as many galvanically isolated barriers. I need to go with a larger panel and everything else. A lot of those arguments have gone away with the recent developments with products that are in the marketplace.
Yeah, and this is one of the reasons why we don't manufacture isolated Zinabel any longer, because the cost factor is no longer an issue. In fact, we have many customers when you have to use 2 Zinabel because you have double wiring, you cannot afford grounding on one of the wiring. The cost is more, and the width is more. Okay, so we have one more poll. This is a tricky one, so I'll launch the poll. We said dedicated grounding is required for galvanic isolation barrier. And what is the question? Is it dedicated low resistance ground required? I give you an answer already. Well, yes, it is required, but okay, is it dedicated low resistance? No, this is well. I honestly, I have not been. I used to run a lot, up to a month ago, I was running and skiing, and I had to stop, and I realized it's taking a lot of effort to regain my strength. And here I got to regain my brain ability. I went by memory, but I did feel it. I should just write a question. So is a dedicated low resistance ground required in a galvanic isolated barrier IS installation? And most of you guys are correct in the reply. I will show you what you have answered. And Paul, it is not required.
That's correct. It is a little bit.
As soon as I saw it there, I remember, it must be less than 1 ohm. I thought that was the answer, but I did not read the question.
Excuse me. Yeah, no, it is somewhat a trick question. So a dedicated low resistant ground required for galvanically isolated.
It's a big issue, the grounding, it's a big issue.
Yeah. Well, and some of you may be involved in the offshore markets when you start grounding.
But also keep this in mind. You have to do testing. You have to do maintenance on the system. You have to check your grounding once. And I don't remember we discussed this one, maybe every 3 years or so. There are periods of time when you have to check. To check the ground, you mean you have to physically disconnect it from the barriers. Otherwise, when you check, you blow the barrier fuse. So it means you have to either shut down. Make sure the plant is, there's no gas presence and so on. Otherwise, you have to build redundant ground. So I've seen also redundant ground built. So the cost of that ground can be, a lot more than the cost of the barrier.
Right. So yeah, that's.
Furthermore, it does not allow you to have isolation. So meaning you have to have isolation of the field device. Otherwise, okay, stop share the result, close this. These are our contact details. Now we have some question and answer let me share my screen if I'm able to today. If I remember how to do that. God, I can't believe presentation, where is it?
If you need me to do it, I'll be happy.
Okay, here it is. You guys see it? You see something, Bob?
I see it.
Okay, great. So through registration process, we had some questions, so we tried to put those together here. So we have 10-15 minutes. We can run those. And again, guys, if you have any questions, just type it in. So first question we had was multiple barrier wired in series and parallel. What are the calculations? As you guys know, when you create a multiple circuit, for example, the typical application could be you want to put more power into a solenoid valve and you put in parallel to barriers. You get more power, of course, because there's less resistance, but things changes. So what is there are some examples here, I see, and depends, you have to have the sum of the voltage or the sum of the currents or the sum of both voltages and currents. I know, Bob, you prepared this answer or?
Yeah. I think is it the next?
Next. Okay, here we go.
Yeah, there we go. So if we do a single supply, our associated apparatus, again, that's our barrier. Our output on that is 28 volts. And there's our device in the field. Well, hopefully, we have enough power that's sufficient. But if we go to the next slide, so we may have two supplies series connection, right? So now our output is 56 volts, 93 milliamps going into our device. So there are ways of doing this, but we have to this. Now, in this case, we have two supplies with a parallel connection. So what we're increasing in this case is the power, but not the voltage. So there's ways of doing this as well. And sometimes you'll actually see this all incorporated into a single associated apparatus where you might have a multiple channel barrier. GMI manufacturers barriers that have, two or more channels. Depending on how you wire it up, you can actually increase the amount of power that's actually allowed. And then, of course, it applies parallel connection. So there's different ways to address this. And I think this was a question that somebody had that sent into us that just asked, how do we address this?
So this is last case where you increase both voltages and current because they are all going into a single apparatus, right?
Correct.
So you have two barriers driving, for example, the power circuit, a 4-wire device, something like that.
Something like that, yeah. This would be a little uncommon, but it is.
Okay, maybe I remember there's a question that might help us understand this a little better later on. So, which is this one? Please explain about entity concept and give us some examples. So, Bob, earlier you talked about the fact that the barrier is, comes in the package with the system. You have the wires and also the field devices to be accounted for.
Right. So yeah, we talked a little bit about this before, but if we go down and we look at simple apparatus, so we want to define what is a simple apparatus, and basically that's the information right there. It will not generate or store greater than 1.5 volts, 100 milliamps, 25 milliwatts, or 20 microjoules. So again, an RTD, a switch, resistor, those are all considered to be simple devices. And here's the important thing to note about simple devices. Simple devices generally, and I hate saying things absolutely rule of thumb worldwide, but generally a simple device does not require certification, meaning that it doesn't have to have an ATEX or an IEC-EX or a North American class division or anything like that. It can be a general purpose unit. Now, IS apparatus, they do require certification. And these are devices that can store energy, which again, could be transmitters, valves, proximity switches. Well, proximity, I'm not sure what proximity, a switch is.
Proximity, no, I guess that means, it's
I don't know.
No, proximity switch, yes, like an Amur switch. You have certification for the same.
But generally, it depends. A proximity switch can be a simple device, but it can be also energy storing too. So
you have 3 wires, proximity switches. You have inductive capacitor. There are some of them which are carry certification. In fact, most of them carry certification.
Right. And then, of course, the IS associated apparatus that does require the certification, and that is considered to be the barrier. One question that we did have before, do the barriers have to be installed in a safe area? The GMI barriers, as an example, are actually certified to be installed in a zone 2 in a suitable enclosure. But if they had to go into a zone 1, you can actually install the barriers in a pressurized PXB enclosure, or you could put it into a flame-proof EXD type enclosure.
Yeah. So basically, I guess the concept here is that the field devices, whether are simple devices or certified unit, along with the associated apparatus, which are the IS barriers, whether are Zener or isolated, and the wiring required to do some calculation. That were the same what you explained earlier, which we have to do. Change this calculation if you have combination of barrier going into a same field device. So this is basically you have to, the concept, I guess the barrier concept, the basic concept is to limit energy. but to what level, to a level that the field device is suitable for.
So entity, yeah, and the important thing to remember with entity parameters, so it's basically saying, look, I have this field device by this manufacturer, and I want to use this associated apparatus from this manufacturer. So I take the entity parameters from the two different devices, and then I compare them myself. Now, in the U.S., a lot of times, historically, because we had not used IS in the United States as much as other people around the world had, and you would usually find a control drawing that would be put out there by the manufacturer of the field device, and in the control drawing, it would pick out and say, use this device because we've already done the entity parameter, or we've checked those entity parameters. But in the real world, there's no reason why you cannot make that selection yourself. You can go, for example, and there you go.
A software, or a packet. We have a question, Bob, which is it's something we came across only in some part of the world, but I don't know if you have an answer for that. I know that we came across. So basically, there's a requirement that says when the inductance is more than 1%, the inductance of the barrier has a certain value over that of the field device, you have to reduce by 50% the parameters. So you're basically reducing the distance of the cable that you can use.
Yes.
And it is written somewhere in the IEC standard.
Yeah, yeah.
And we know that our Japanese certification, we had to reduce the parameter, drastically reduce compared to ATEX certification because of this ruling. But I'm not sure why.
Yeah,
it is like
that. I've heard of it. And I tell you what, I've got your contact information. I will do some digging on that. And but it is a good question. I've heard of it, and I know that is true, but I'm not sure why.
Yeah, but only so far in our experience, we sell our product globally. Only in Japan we came across this issue. They basically apply the wording, as we say, to the single syllable, that they say, okay, this is what it says, this is what I do. I don't care the context and why, because everybody else is saying, no, it doesn't apply in a normal situation, blah, blah, blah. But we will investigate on that. I will ask also our certification engineer, Roberto, maybe to give us, we'll send you an answer. Okay, we do have some more questions.
Yeah.
As part of the regulation, do we need IS calculation and DSD dossier for simple devices?
Yes. Yes, you do. Yeah, it is a requirement to create a DSD basically for all IS loops. So you are required to create this DSD. Now, again, that's based upon the IEC standard. And again, the details on that are going to be in 60079-25. Now, there's different formats, and they show within the -25 standard how the format can be done. But yes, you should have calculations done. But what I have seen and what is very common, you might have a control drawing that has maybe 20 different transmitters, but you're using the same exact transmitter, you're using the same exact barrier. You have a maximum length of cable, say 1,000 meters or 500 meters or whatever that calculation length is. And then on your control drawing or your DSD, you'll actually have tag number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, so forth and so on. So instead of creating 20 drawings, you would create one drawing with 20 tags, so to speak. But yes, it is a requirement to do a DSD. And I'll be honest, when I go and do inspections on intrinsic safety, that's one of the first questions I ask is, can I see your DSDs? And usually I get a look of shock because people don't know what I'm asking for. And that's okay, we understand. So we have to create, we'll wind up creating a DSD after the fact and put that in that technical file.
So Carl here is questioning our ability. Well, we mentioned we can do some calculation to increase in parallel or series the barrier solution. So it says, I thought of doubling up barriers would defeat the safety concept. It does not. It is possible. You have to make some additional calculation. I believe there is one little, if I believe that you cannot, it becomes a different, it's from IA, it becomes an IB device, if I remember correctly. You cannot go to.
Well, yeah, it can be done. You're right, Carl. It's not necessarily something you could defeat the purpose, obviously, of the loop, but that's why you do have to do some calculations, and there is some additional items in there. I didn't want to make it sound like you could just do that arbitrarily. So if I said that, or anybody took that from that, it's not my intent.
No, but there is you have to do some calculations. There is a way to follow. Okay, right. Let's see. So, okay, this is a question we had, but I believe we discussed these differences. I can run through this very quickly because we're running out of time here. So basically the con and pros of Zener versus Isolator. I think Bob gave you this answer. But beside cost, which it's always coming up as an issue. On the other hand, Bob, we did a project very recently. The customer in Brazil is buying our competitor Zinabel, which you will not mention. And I was worried about the cost issue. So I said, well, give me target price. And I was very surprised. Our cost was lower with an isolator. So, but you have to consider the total cost, total cost of operation. You have to worry about the grounding. Also, because we have multi-channel barriers, now we have up to 8 channels in a single barrier. So you reduce the amount of space even compared to Zener barrier. There are some applications, honestly, where Zener barrier are today the only solution. Because Zener barrier, the advantage of a Zener barrier is that it can be used within the voltage power range that it can handle with any device. It's just 2 wires, a fuse, and a resistor. If you have a special device, say, for example, a displacement sensor or something very unique, or rather that transmit a signal which is complex, the isolated barrier needs to take that signal and transfer through a transformer. So it has to manipulate the signal and rebuild the signal on the other end. So it needs to be specifically designed for that. And there are some very rare applications out there where isolated barrier have not been designed for yet, because the market is very limited or whatever reason,
Yeah. No, that's a good point. That is a good point, because there are some, anyway, you already said it.
We have more questions, or is let's go on. How do I connect a safety ground on a Zener barrier? Well, I'll let you answer, Bob.
Yeah, and so I mean, this is very common. The picture on the right-hand side, so you see an example of a Zener barrier, and obviously one of the things that people forget about is that obviously the Zener barrier is mounted to DIN rail. That DIN rail is part of the ground, if you will. So we want to make sure that the DIN rail, when we are doing Zener barriers, if it's attached to the enclosure itself, well, we need to make, which obviously would have to be attached to the enclosure in some fashion. But we will want to use insulated standoffs to make sure that that DIN rail is not actually in contact if we're using a metallic enclosure of some sort. So that's typically what you would do on the mounting of Zener barrier type products. And you would not generally mount those on the same DIN rail as your other devices.
Okay, we'll stop in an answer here. Do I have to keep IS and non-IS wiring separated for isolator or for barriers? And can I mix IS and EXD wiring? Well, we said we can mix the two technology, but the wiring, how about the wiring, Bob?
Yeah, regardless if you're doing Zener or galvanically isolated, we must maintain a separation between IS and non-IS. And basically worldwide, the standards are all pretty much the same. In the United States, we say 2 inches. In the international community, we say 50 millimeters. Now that can be done via free air. It can also be done via partitions. There's different ways of doing it, but this is one of the big things that we need to make sure that we remember is that we must have a segregation between IS and non-IS within inside our panels. The same thing when we're taking running of cables outside of the panels to our field devices. as long as this is a generality again, and it may be different in other parts of the world, and of course clients will go above and beyond. But what the standard will basically say, if we're using an armored cable or we're using some sort of shielded cable, either for our instrumentation or our IS or both, then that 50 mil separation between cables, we don't have to worry, meaning that we can run IS and non-IS cables within the same tray or wireway or whatever right next to each other. Again, as long as one or both have shields or armors to make sure that we don't have inductive currents transmitted from the non-IS to the IS. However, on the other hand, oh, go ahead.
No, sorry, Bob. So what about, we have a live question here. It says, what about the segregation between EX and R, EXIC, which I'm not sure what they are.
Hold on.
Is an EX and R circuit?
Bear with me.
Yeah, you can read.
Oh, yeah. Is the requirement for segregation cable also valid for EXNR, EXIC? So EXNR is restricted breathing, and restricted breathing is not an intrinsically safe concept, if you will. So generally, it's not a requirement of segregation because you're not using IS for EXNR. On EXIC, yes, absolutely. You do have that requirement for EXIC. That requirement applies to IA, IB, and IC circuits.
Great. So here is the point we got. You talked about this segregation, and we did not discuss this, but it's a question I posed to you guys. What is the distance requirement for this? What is the segregation requirement? 25 mm, 40 mm, 50 mm, 80 mm? If you're dealing with the IS, this number should be very familiar to you. And I got too many things open here in the computer. I start losing control. So, okay. So, this segregation, for example, there's a limit on the size of a barrier we can design, because we have to keep the segregation between the input and the output wiring, between the two sides, the IS and non-IS side. And, that's why you cannot go smaller than this distance. So and so far you have all answered correctly. So let me end the poll, share the result. It is 50 mm.
I didn't know we had a poll for this. So
I didn't know either. I saw it coming up and I looked it up as wow, somebody prepared it. So very good. Yeah, it is 50 mm. Great, guys. So we have more. Okay, sorry, this question we answered live. Fine. Done. Next. Too many things. This is an example of an incorrect installation. Right?
Yeah.
You're not supposed to do things.
Yeah, right. So I mean, on the one on the left-hand side, when we start looping around our individual core conductors, we violated that 50 mil separation, right? If we look on the panel on the middle there, we can see obviously it looks like cables on the right-hand side are marked light blue, so that's telling me it's IS. We have certainly segregation between the cables, but once we get inside the panel, now all of a sudden it's all hell break loose. On the right-hand side, that's kind of an interesting one. We have some barriers. We have a partition. On the left-hand side there's actually some sort of contactor or breaker or something that's obviously non-IS, and we have some IS circuits.
Sorry.
Oh, no
I was
problem.
trying to annotate, but I cannot do that while I'm presenting. I don't know how you do it.
We just have some IS. This is actually one that I did an inspection on, and unfortunately, that was a barrier gland that was going right out of that particular entry. That was some IS circuits, and they defeated in effect the 50 mil separation. So that was unfortunate that they needed to remove that gland and cable and do all that good stuff. So,
well, we're running over our time. We do have a few more questions if you guys want to stick with us. Let me see. We had, what about using Zener Barriers with the Grandest sensor? We said this earlier, I believe we cannot do it. Right, Bob?
Yeah, no. Correct.
We cannot do it because if we use a Grandest sensor, then we have two paths for that full current to go either in the, the IS ground or the field sensor grounding. It's an issue, for example, with thermocouples, a simple device, nobody think of, you put a barrier and then they are within a jacket, there is vibration, this thermocouple gets grounded to the jacket and
there you
safety is gone.
Yeah.
Very simple, very problematic. You answered this already through the webinar. Can I install a barrier in a classified area? Yes, you can, but you must use a proper enclosure or use a barrier which is designed for installation in the classified area, such as GMI. You can install in Division 2, of course, providing an IP54 enclosure because some kind of cabinet. Well, that's an interesting question. Should I worry about SIL? Well, we're not talking about SIL today, but let's see what the answer says. There are some advantages in SIL, of course, but it's not a requirement, right, Bob?
No, it's not a requirement. Barriers do not require, unless that, it's not a requirement that's written down within any of the 60079 standards or in the wiring regulations that I've seen. The advantage is basically I guess basically the failure data rate that you've got under a SIL device is that that this product has been tested and certified and it is so X reliable, if you will. And so obviously IS is a safety critical device. So the fact that an IS barrier actually has a SIL rating is a good thing. It's not mandated. It's not a requirement unless a client says it's a requirement. But the standards don't tell you must have a SIL rated IS barrier. But it's not a bad thing.
Yeah, it's not a must. It's just typically a SIL certified component. It's a better component, or at least the specifications are correct.
That's right.
So are they mainstream? Okay, well, this is exactly a question we go live to right now. It says, where can we not use a Zener barrier? No, well, this is when we cannot use a barrier. Carl is asked if there are applications where galvanic isolator cannot handle. And as I mentioned earlier, there are some installations, for example, take AC circuitry. I came across an installation once where you have a couple of copper bars going down in a tank, okay? And they are reading for, it's just level switches, very simple.
Right.
And you have to run AC current, because if you run DC current, you have some kind of oxidation, some kind of chemical reaction. And so you need to have AC current. But an AC barrier, it's not a lot of voltage, 24 AC. But for example, we do not make an isolated barrier that can run 24 volt AC. So you have to use a Zener barrier. Okay, so but Zener barrier or isolated barrier have their own limitation, as you explained earlier, right, Bob?
Right. Yeah. No, there's certainly some applications still out there, and again, the signal speed. I think that's where we've run into an application here or there. But generally speaking, almost, it's 98% of the applications we've been able to do with a galvanically isolated product. That wasn't always the case, but as technology has gotten better.
For example, we have something else that typically it's a barrier used on, and it just came into my mind. It's for strain gauges, for weights, scaling. Typically you have 6 barrier, and this is because what you need millivolt to millivolt. So you don't want to somehow condition the signal, because your scale on the other end is designed to read the strain gauge. But a few years back, we developed a barrier, which is an isolated barrier, and transparently transfer the same signal of the strain gauge on the safe side through the isolation. Of course, it had to be specifically designed for that application, but it's a large application, so we did it. So it's not that it cannot be done, it's just it requires sufficient momentum to develop a barrier. Okay, so I think we are close to the end of our presentation. We're like 10 minutes late.
I think we've already done this one. Yes.
Wire and difference, we discussed that.
Yeah.
Here's some more examples. We have a question here says, would you like to know about fundamental? Oh, okay, yes. Every time we do a webinar or something, somebody asks for, can we do a webinar on something else? And of course, we do. We have many, many different topics of our live webinars. You can go online and see our schedules. And if you missed the webinars, they are registered and you can see them or you can review them on YouTube channel. Now we have one last poll for you guys. Let me see if I can find it, which is how Bob did today. So how did we do? Okay.
You did a lot of it today. You were fantastic.
Well, as I said, if my vote is immediate and yours, you get your votes and my vote.
No, not at all.
Today, honestly, guys, I hope none of you had this experience of COVID. I was not that bad. It was a week of quite bad, but it really changes everything in you. You're not yourself anymore. You need some time to readjust.
I'm glad you're back.
Yeah. Okay, great. So most of you have told us excellent and good. So share result. Thanks again. These are contacts again, and stop sharing result. Close this. Close this. Okay. So Bob, thank you again for the webinar. We'll try to get back to those guys that have the question we could not answer. We will send you a mail. You will get a copy of the presentation. Each one of you that register will get a copy of the presentation. Anna will send you. And that's about it. We have a few more live questions. I'm not sure if you want to answer. Do the intrinsically safe barrier or isolator affect the sensor speed? For example, transmitter 4 milliseconds, yes. The barrier has its own response time, which you have to add to your total response time. It's not we try to design them, super fast, but application, for example, where you have rotating equipment, such as gas compressors, we had to develop a special barrier, very, very fast response for thermocouple. But typically you have 50 millisecond response time through a processor. We had to develop one for 5 millisecond response time. We did it, but it has some limitation. You cannot do compensation and stuff like that. Okay, thanks, Bob. Thanks again. Thank you, guys.
Thanks, everybody.
Thank you, and we'll talk to you soon. Let me see what I have to do here. Push the end button. Ciao, guys. Ciao.